In the last couple of videos, we talked about the ideas of how, first, if you're given features for movies, you can use that to learn parameters data for users. And second, if you're given parameters for the users, you can use that to learn features for the movies. In this video, we're going to take those ideas and put them together to come up with a collaborative filtering algorithm. So one of the things we worked out earlier is that if you have features for the movies, then you can solve this minimization problem to find the parameters theta for your users. And then we also worked out that if you are given the parameters theta, you can also use that to estimate the features x, and you can do that by solving this minimization problem. So one thing you could do is actually go back and forth, maybe randomly initialize the parameters and then solve for theta, solve for x, solve for theta, solve for x. But it turns out that there's a more efficient algorithm that doesn't need to go back and forth between the x's and the thetas, but that can solve for theta and x simultaneously. And here it is. What we're going to do is basically take both of these optimization objectives and put them into the same objective. So I'm going to define a new optimization objective, j, which is a cost function that's a function of my features x and a function of my parameters theta. And it's basically the two optimization objectives I had on top, but put together. So in order to explain this, first I want to point out that this term over here, this squared error term, is the same as this squared error term. And the summations look a little bit different, but let's see what the summations are really doing. The first summation is sum over all users j, and then sum over all movies rated by that user, right? So this is really summing over all pairs ij that correspond to a movie that was rated by a user. It's a sum over j says for every user, sum over all the movies rated by that user. This summation down here just does things in the opposite order. This says for every movie I, sum over all the users j that have rated that movie. And so, these summations, both of these are just summations over all pairs ij for which r of ij is equal to 1. It's just summing over, all the user movie pairs for which you have a rating. And so those two terms up there is just exactly this first term, and I've just written the summation here explicitly where I'm just saying, the sum of all pairs ij such that rij is equal to 1. And so what we're going to do is define a combined optimization objective that we want to minimize in order to solve simultaneously for x and theta. And then the other terms in the optimization objective are this, which is a regularization in terms of theta, and so that came down here. And the final piece is this term, which is my optimization objective for the x's, and that became this. And this optimization objective j actually has an interesting property that if you were to hold the x's constant and just minimize with respect to the thetas, then you'd be solving exactly this problem. Whereas if you were to do the opposite, if you were to hold the thetas constant and minimize j only with respect to the x's, then it becomes equivalent to this, because either this term or this term is constant if you're minimizing only with respect to the x's or only with respect to the thetas. So here's an optimization objective that puts together my cost functions in terms of x and in terms of theta. And in order to come up with what's just one optimization problem, what we're going to do is treat this cost function as a function of my features x and of my per user parameters theta, and just minimize this whole thing as a function of both the x's and a function of the thetas. And really the only difference between this and the older algorithm is that instead of going back and forth, previously we talked about minimizing with respect to theta, then minimizing with respect to x, minimizing with respect to theta, minimizing with respect to x, and so on. In this new version, instead of sequentially going between the two sets of parameters x and theta, what we're going to do is just minimize with respect to both sets of parameters simultaneously. Finally, one last detail is that when we're learning the features this way, previously we have been using this convention that we have a feature x0 equals 1 that corresponds to an intercept term. When we're using this sort of formalism where we're actually learning the features, we're actually going to do away with this convention, and so the features we're going to learn x will be in Rn, right? Whereas previously we had features x in Rn plus 1, including the intercept term. By getting rid of x0, we now have just x in Rn. And so similarly, because the parameter theta is in the same dimension, we now also have theta in Rn, because if there's no x0, then there's no need for a parameter theta 0 as well. And the reason we do away with this convention is because we're now learning all the features, right? So this means that there's no need to hard code a feature that's always equal to 1, because if the algorithm really wants a feature that's always equal to 1, it can choose to learn one for itself. So if the algorithm chooses, it can set the feature x1 equals to 1, and so there's no need to hard code a feature that's always equal to 1. The algorithm now has the flexibility to just learn it by itself. So putting everything together, here's our collaborative filtering algorithm. First, we're going to initialize x and theta to small random values. And this is a little bit like neural network training, where there we were also initializing all the parameters of a neural network to small random values. Next, we're then going to minimize the cost function using gradient descent, or one of the advanced optimization algorithms. So if you take derivatives, you find that the gradient descent updates are like these. And so this term here is the partial derivative of the cost function. I'm not going to write that out with respect to the feature value xik, and similarly, this term here is also a partial derivative value of the cost function with respect to the parameter theta that we're minimizing. And just as a reminder, in this formalism, we no longer have this x0 equals 1, and so we have that x is in Rn and theta is in Rn. And in this new formalism, we're regularizing every one of our parameters theta and every one of our parameters x, and there's no longer this special case theta 0, which was regularized differently, or which was not regularized compared to the parameters theta 1 down to theta n. Okay, so there's now no longer a theta 0, which is why in these updates I did not break out the special case for k equals 0. So we then use gradient descent to minimize the cost function j with respect to the features x and with respect to the parameters theta. And finally, given a user, if a user has some parameters theta, and if there's a movie with some sort of learned features x, we would then predict that that movie will be given a star rating by that user of theta transpose j. Or just to fill this in, we're saying that if user j has not yet rated movie I, then what we do is predict that user j is going to rate movie I according to this. So theta j transpose xi. So that's the collaborative filtering algorithm, and if you implement this algorithm, you actually get a pretty decent algorithm that will simultaneously learn good features for hopefully all the movies, as well as learn parameters for all the users, and hopefully give pretty good predictions for how different users will rate different movies that they have not yet rated.